Hello, my name is Jessica Abaza, and I'm here to talk about Excel report number 3. It's the last module of my class, and let's just dive right in. So scenario 1 is about theoretical probability and empirical probability. We had learned a couple of things in Excel, and which the sigma symbol here off to the left means the sum, and this pi symbol here means to multiply. That's just so you can understand some of the formulas that we're going to be talking about in this video. We also did composite numbers, prime numbers. If you're familiar with those are kind of the numbers we worked with in our dice. Over here in theoretical probability, it's what we expect to happen, and no experiment is actually conducted. So this is if we roll one dice here, and obviously if we roll a 6-sided die, it has 6 sides, 1 through 6. And then here we have die 2, which also has the same set of numbers. So if we were to roll and say we were to get a 1-1, well, it'd be the sum of 2, you know? So 1 times 1 is 2, 1 plus 1 is 2. Okay, anyway. We continued on with prime numbers, and we just did this as if, it was set up. It was very, very set up, strategized kind of way. Over here on this slide, is it this slide? No, this slide. It would be probability sampling. I just wanted to go back and make sure I had the right terminology. This would be probability sampling. Whereas over here, this was random sampling for empirical probability. And most of the time when that's used, it's based on what's already happened. So restaurants use this a lot, actually. They order food based on what their customers order off their menu. I've worked in restaurants, so that's working with chefs. That was pretty much what we did. Down here I have these histograms that kind of represent the data, and these charts over here to the right for the empirical data. And back over here to the theoretical probability. Once we've set up our chart here, this gives us the probability of it happening in fraction form. Then we put it in decimal form and percent form. So what we actually did here, our little formula, we locked E, so that way it would continue to find the sum of the 2 dice. And voila. Our next scenario is biased binomials. Binomial experiments satisfy 4 conditions. So it has to meet 4 conditions in order for you to use this type of theory or experiment. It has a fixed number of trials, so you're gonna do X amount. So like when we rolled the dice, we rolled it 36 times, so we could get 36 different outcomes. Or like when we did the random generation numbers, we did it 6 times, 60 times, 600 times. So each trial is independent of the others, so it has its own independent die 1 and independent die 2. Then we have there are only 2 outcomes, so it's either going to land on a number or not a number, like heads or tails in coins. The probability of each outcome remains consistent from trial to trial. So it has to kind of like have somewhat of a standard correlation. Then as we go through here, we have this is our formulas we used. And this one down here is our Excel formula that we used in here to get these fancy numbers. So first, we did a scenario with a student guessing a 10-question quiz. And this person didn't really study and they just guessed through the whole thing, but they miraculously got an 80%, which lucky them. I wish I could do that. To test this, we used our distribution formula variable identifications. And up here to the top, B stands for the binomial probability, which he got 80% correct. So that's where we got this 8.0. The P is 1/4. Total of number of success, pass or fail. We got that because of this percentage here, which was our combination formula, as you can see up here at the top. And when I highlight it, it tells you which numbers I plugged in each for this formula. So I did equals combination N, which is 10 down here, comma B, 28, which would be my X here, and so on and so forth. And that was our percentage of pass, I believe. So even though it's a possibility you could do this, it's not really likely. You better be having a lucky day. Kind of the same outcomes within lotteries. We did an example of the Illinois lottery. And again, here's our possible winnings, 0 up to $1 million. And we did possible outcomes. So if we buy a ticket, we're automatically out $5, right? Because if we don't win anything, we spent money and it was a waste of our time. But if we win $5, we broke even. We could go, man, maybe gambling's not for me. But if we try a third time, let's say we bought another ticket, $5 again. But we won $5. Actually, we won 10 because we put $5 in. So now we made $10 profit off that winnings. So here we have our probability in fractions. Again, we did the sum of all of these numbers to equal this, I believe, right? So we changed it to fractions, and here's our outcome here. We have, if we were to spend a bunch of money, eventually we would have a constant profit of negative $1, almost $2. So we're losing money more than we are getting money. But think about all the kids in Arkansas and non-kids, non-traditional and traditional students in college that gain access to scholarships that grant them better job opportunities. So can't really complain about that, right? Excuse me. Betsy's going to say something. So again, the next part of this challenge was to see where does our state lottery go. And we did Arkansas. Well, I chose a couple of different ones, but the primary one was Arkansas, just to see kind of like where ours went. I found this chart, and here's my source right here. You could see the website pop up when you hover over it. And I chose Florida because it's somewhere. I kind of just chose these based on what I thought would make the prettiest looking pie graphs because they seemed well balanced, and that would be stratified, I believe, sampling data. I'm kind of correlating it with all of each other after kind of going through all these scenarios. I see where they all tie together, and that's pretty awesome. So in Arkansas, 76% of it goes to prize money, 15% to state funds, and 9% to administration. When we add all these percents together, equals up to 100%. We can never have more than 100% of anything. And the same happens. You can see my stats for Florida and Colorado. Colorado has a little bit more of a chance of winning prize money. Look here, 80% compared to Florida and Arkansas, which only have 76%. So that's pretty awesome, seems to me. Moving on to Bass. Bass. I always call it Basmati Index. I think it might be an art thing. I have no idea. But it's Basmati. See, look, tongue-tied. I cannot say this for some reason. Body Mass Index, BMI. So I've been familiar with the chart I found in my previous Excel report. Actually, it might be in my house. Yeah, this one. This is where I first kind of looked at this for the first time because I was curious about my obesity. I know I'm obese. Luckily, I do not suffer from diabetes or high blood pressure yet, but if I continue the way that I live, it will eventually turn into high blood pressure because it is genetic in my family. And I'd rather it happen at an older age rather than a younger age because I have a daughter that's young and I want to be able to keep up with her. And I also don't want to be straddled down to prescriptions for the rest of my life. So here we did a bell curve for that, or at least I did, for my sugar consumption, and I know that that plays a really high role. As you can see, just to prove a point, every once in a while I have a root beer, which is terrible for me, and I know this, but it's still delicious, and addiction is an addiction, and cutting it cold turkey is kind of hard. But I know what I need to do. So back to this, I chose down here, my two people. I chose my husband, and then I chose my cyber husband, or at least I wish, Deadpool, Ryan Reynolds. So we've worked with mean and standard deviation before, and then we had to do confidence intervals, and I got this off of an internet source that was provided for me, and that's how I got these two numbers, but they were important because when I plugged them in to my Excel for my formula here, as you can see, I used my mean and my standard deviations for this kind of stuff. Here is the women's chart. Here you can see this line here represents the percentile rank. If you can see that. And then here is our standard deviation number. We worked with this in a previous Excel, so I don't feel like I need to go over that again. But we did use this. We kind of got this based off of another graph because these seem pretty common throughout. We also used this is where I got those numbers, 13.6. We also studied z-curves, probabilities, and confidence intervals. These are all same numbers. They're just kind of reported a little differently. So like this number and this number, it's just kind of like separated in different sections, even though it's still the same percentage of that same percentage. It's almost always reported rounded up to the nearest tenth, and I made these notes that way I would know how to graph in the future a little bit better. The x-axis is a horizontal asymptote, meaning the curve comes down on the side but never touches the x-axis, and then you can see right here actually, this area right here. See how it doesn't touch this line? Yeah, that's what that's talking about. That's an asymptote. Never touches. See, it gets really close, but there's, I'm sure, a tiny, tiny little section in there where it's not touching. You just have to zoom in. Z-scores are, you know, your personal score, where you lie on that bell curve, that normal distribution curve. Just see the Z curve right here. This little line, I can move it. I told you I could move it. Anywhere I move it, that's going to represent my data that I'm picking. So mine was for me. I have another one for my husband and another one for Ryan Reynolds. We used this lovely chart provided for us on Google to figure out these numbers here, which let's see here. Yeah, here's the formula. We used a normal distribution formula, and we plugged in for all of this X variables and so on and so forth. Where's the formula? I was trying to find like where usually I have a legend, but I don't have a legend. So here's X right here. And let's see. Here is our mean, which would be the second part of our formula, and then the standard deviation, which would be the third part of our formula. And of course, we used false always in Betsy's class, except for in the homework it required us to use true. So when we talked about body mass index, it's a unit of measure used to measure the body's fattiness level. The relationship between the average, standard deviation, z-score, and confidence intervals is all represent data of the collected samples given us what our samples have in common. In this scenario, we reach the BMI averages of women and where my BMI is on the chart, as well as 2 other people. I made a z-score for each of us, and I compared our BMI to the average in my state I live in. So that's where this confidence interval is. It was my state's confidence interval, well, what we all have in common. And then I compared both of Matt Abaza's and Ryan Reynolds to Arkansas State men. See? Anyway, that's how I did that one. The next scenario is about buying houses. Yay! Can't get there yet because I don't have that kind of money. But if I did, I would use this. It was interesting to find out what actually it means to put a percent down, how much of a loan you're actually taking out, and how many years. And we also included data if we were to make extra monthly payments, such as 50 and 100 and none. Here's my legend. Here's all of my charts. Here, I can still keep this information in the future. Say there is a house in town that I really want to buy. Oh, crap. All right. All right. See how all of it zeroed out after I did that? Let's say it's downtown. It's kind of in the hood. So it only costs $34,000. I have to put 8% down on this house, let's just say. That means I'm going to put $2,000 down because it would be this times this percent down times cost gives me $2,720 down, which means I only need a loan for $31,000. And my rate of interest would be 5%. So my monthly payment is going to be here about $590.29. If I were to choose a 5-year plan, which the interest would only be $4,000 here. If I chose a typical $20 plan like most people do, my monthly payment would be $206, which is pretty cheap. I like that idea better. With an annual payment, which means yearly, it's about $2,500, and the total cost of this house by the time I get done with my interest loan is going to be almost $50,000, and the amount of interest I've paid is $18,000. Let's see here. Let's change this to 206.43. So now we have a monthly payment of this interest, and this was just using the all right, so this one would be, it would be this plus an extra $50. And see how it shows us what's post change. And then this one would be this plus an extra $100. Yeah. See, it changed. We just had to get all the way down here to the bottom. So that's how that works. And then here is our chart data based on that stuff. Then we learned about subsidized and unsubsidized loans, which is depressing to talk about. I hate that college is so expensive, and I feel like maybe our government should try to do something a little bit better about how affordable college is for students. But if it wasn't, then we wouldn't owe all this money to them, so it just feels like a never-ending dying loop. Here we learned how different sampling can affect your view. Like it could project an information that's not entirely accurate. For example, random sampling, if you're just to like collect a bunch of random stuff and you don't have an equal number of all the items you're trying to test, then you're going to be testing more of one independent subject than the others, and it's not going to really give you accurate information because you have more test subjects in that area. But when it comes to, we used political parties for Donald Trump. Here, if we set up each, say we sampled the area and only Republicans voted or answered this sample, same for this independent and Democrat. Of course, these are going to look not entirely accurate because we only Republicans have rated for President Trump in this and independents in this and this. So we had graphs that represented it. I'm sorry, I'm kind of tired. I've been exhausted from finals all week and my voice is starting to go out a little bit. So, and it's starting to hurt, which is why I'm trying to hurry up and get through this video. My apologies. In this report, we talked about different types of sampling, and the types of sampling were random sampling, and that's if we randomized everyone or everything has a chance to be equally picked. Random samples are usually fairly representative since they don't favor a certain member. So it can't be biased because it's completely random, kind of like the dice rolling. Stratified sampling is volunteer sampling, which is what we observed in the independent ratings and Democrat ratings. And that's when a population is first split into groups, and overall samples consist of some members of every group. The members of each group are chosen randomly, and then a stratified sample guarantees that members of each group will be represented in the sample so that the sampling method is good, and we want the same members from every group. Convenient sampling, researchers choose a sample that is readily available in some non-random way. This is a terrible way to sample because it could be biased. Researchers use convenient sampling not just because it's easy to use, but because it's also other research advantages. Conditional probability is a chance of something might happen based on what has already happened, which we were talking about restaurants and stuff for that. Since it's impossible to collect data from every individual person on Earth, it is simpler to pile them into groups with similarities and test the individual groups. It's also important to use data that's relative to another, otherwise you might just get confusing results. Kind of like how we've compared autism and corn. I guess the idea was the pesticides in corn was causing autism for some reason. Now, the last part of our project was the 3D graphs, which I really enjoyed. Here we could change the perspectives, which was pretty cool. 3D rotation, here we go. So as you can see, if you play with it, it can make your graph look really different. This is a kind of like a second and third point of view, just so you know. Turn it. Now it's in first point of view. But yeah, you can see how it changes. This is my favorite graph. This I was kind of trying to play with it. I used negative numbers to try and like create really large dips in my graphs. Here I created a hole in the center of one. These are really cool. I'd like to go on and maybe create more kind of like similar to this. Anyway, a 3D graph's just a computerized sculpture, pretty much. The computer runs a number system language and certain combination of numbers to cause peaks and drops in the graph shown in the section, which are what I was telling you why I use negative numbers to create peaks. That way you can really see drastic things in this 3D graph. Anyway, that was my Excel report. I also worked. I did a dream report too, my financial report. I was really excited about that. I was serious about reusing this graph and keeping it with me forever because eventually I will need to know how to do that when I go to budget money and stuff. Other than that, I look forward to seeing everyone at Miss Benzie's end of the semester bash. Bring a bathing suit if we're gonna have fun in the pool and stuff. But anyway, I hope everyone enjoys their weekend, their summer break that's coming up, and have a great evening. Thank you so much for your time.